in this session, we introduce the concept of properties of the Fourier transform. As we saw in the case of Laplace transforms, some of the properties that we studied there are also same property that holds for the Fourier transform. So we start by the first property of the Fourier transform, the so-called the linearity property. So the Fourier transform is a linear operator. It's a linear operator. i.e., given two functions, f of t and g of t, and a constant c, then we have one that the Fourier transform of f of t plus g of t is given by the Fourier transform of f of t plus the Fourier transform of g of t. And then two, the Fourier transform of c times f of t is the same as c times the Fourier transform of f of t. We can easily prove this two relationships. So proof. So the first part claims that the Fourier transform of the sum of these two functions, f of t and g of t. So from definition, this will be the same as the integral from minus infinity to positive infinity of now this sum, f of t plus g of t, and then we multiply by e raised to power negative I kt dt. So this is by definition of a Fourier transform of any given function. So these are sum of two. Now we can always distribute this exponential function to these two functions. So this will be the same as integral from minus infinity to positive infinity of f of t multiplied by exponential I k t plus g of t multiplied by exponential negative I k t and then dt. So we are doing that one because functions obey distributive property. And then next, distribute dt to each of these and the integral sign to each of them. So we'll have the integral from minus infinity to positive infinity. I can first write f of t e raised power negative I k t dt plus g of t e raised power negative I k t dt. And then finally, I distribute the integral operator to each of the two functions. Integral from minus infinity to positive infinity of f of t e raised power negative I k t dt plus the integral from minus infinity to positive infinity g of t e raised power negative I k t dt. And you see this one here is the definition of the Fourier transform of f of t, while this one here is the definition of the Fourier transform of g of t. And so we end our proof. Second part, So we want to define the Fourier transform C times f of t. This will be simply the integral from negative infinity to positive infinity, C f of t times e raised to power negative I k t dt. This by definition. And then this being a constant, then this integration, we can always factor out the constant. So this C integral from minus infinity to positive infinity, f of t, e raised to power negative I k t dt. And then by definition, this part is what defines the Fourier transform of the function f of t. So therefore, that ends the proof. Now, let's quickly do an example that makes use of this property. An appetizer. So the example says, find the Fourier transform of this function u of t e raised to power negative t plus u of t e raised to power negative 2t. Note that u of t is the unit step function. So solution for this, I will say the Fourier transform of u of t e raised to power negative t plus u of t e raised to power negative 2t. Now this is like our f, this is like our g function. So the same as Fourier transform of u of t e raised to power negative t plus Fourier transform of u of t e raised to power negative 2t. That's what we have by definition. So Fourier transform of u of t e raised to power negative t is the same as the integral from minus infinity to positive infinity of u of t e raised to power negative t e raised to power negative I k t dt. But remember, this unit step function is 0 for negative values, so and 1 for positive values. So these are the same thing as saying the integral from now 0 to infinity of, now from 0 the u is 1, so just have e raised to power negative t e raised to power negative I k t dt. And similarly, the Fourier transform of u of t e raised to power negative 2t is the same as the integral from minus infinity to positive infinity u of t e raised to power negative 2t e raised to power negative I k t dt, which will be similarly the unit step function is always, remember this is the way we define the unit step function, has two values, 1 when t is positive and 0 when t is less than or equals to 0. So for from negative infinity to 0, then the value of the integral is 0. So we start from 0 to infinity and u will be 1. So we'll have 0 to infinity e raised to power minus 2t e raised to power minus I k t dt. So the integral 0 to infinity, remember this can be written as negative of, so therefore the Fourier transform will be Fourier transform negative t plus ik t dt plus integral from 0 to infinity e raised to negative 2 plus ik t dt. So that this can be written as limit as r approaches infinity of integral from 0 to infinity e raised to negative. Remember, this is 1 plus ik t. This now are not infinity. And then dt plus limit as r approaches infinity 0 to r of e raised to negative 2 plus ik t dt. Now, using integration by substitution method, use substitution method, you find that this will give us a limit as r approaches infinity of now negative 1 over 1 plus ik into e raised to negative 1 plus ik and then t from 0 to t equals to r plus limit as r approaches infinity of negative 1 over 2 plus ik e raised to negative 2 plus ik. Then there's a t here. T is running from 0 to r still. So here, I can always factor out this negative 1 over 1 plus ik. Limit as r approaches infinity. Now, when I put in the upper limit, I'll get this to be r, so I can write it as 1 over e raised to power 1 plus ik r. Lower limit will be e raised to power 0 is 1, so 1, and then plus or minus 1 over 2 plus ik limit as r approaches infinity. Similarly, putting in the upper limit, I'll get 1 over e raised to power 2 plus ik r. Putting lower limit will also get negative 1. Now here, I will have negative 1 over 1 plus ik. Now limit as r approaches infinity of this quantity is 0. Limit of a constant is a constant, so negative 1. Minus 1 over 2 plus ik. Limit of this quantity is 0. Limit of a constant is negative 1. This is meant to be negative 1. So here we will have 1 over 1 plus ik plus 1 over 2 plus ik. So which we can put under 1 LCM. So 1 plus ik and then 2 plus ik So this will be 2 plus ik plus 1 plus ik, which will give us 2 plus 1 is 3, and then plus 2 ik. 1 times 2 is 2, plus 1 times ik is ik. Ik times 2 is plus 2 ik. And then ik times ik. So I times I is I squared, whose value is -1, and k times k is k squared, so it will be negative k squared. So therefore, the answer will be, the Fourier transform will be given by 3 plus 2ik divided by 2 minus k squared plus 2ik plus, so this will be 3 now, because ik plus 2ik. So this is a final answer to that given question. Thank you.